So I guess I should start. So thank you very much for coming to the session about Ethereum blockchain technology. Let me first just introduce myself. So Christoph Jentzsch. My background is actually in theoretical physics, so I'm not a developer by study at least. But I worked then, did my PhD, or not finished it, on working on GPUs and CUDA and programming for highly parallelized systems. And then I moved in summer 2014 to a project called Ethereum. And I will explain you more what this is all about. And I worked for this since summer 2014 until the end of 2015. Then I created my own company called Slockit. And we are working on the connection or the intersection of blockchain and IoT, that we connect smart devices to the blockchain. So this just is a short introduction. So what I want to talk about today is first give you a short but hopefully almost complete introduction in what actually is a blockchain. What does it mean? What are the basic definitions you need to understand in order to understand how such a system works? And then I want to go into a bit more what Ethereum is, which is of course based on blockchain technology. So you may have heard a bit of hype around the topic. So if you are around at other conferences or if you are a consultant at different companies, blockchain seems to be a buzzword which you hear a lot. Everybody wants to build on top of it, but most people don't really understand why and what they get out of it. Some people say it's highly efficient, but then I have to argue, no, it's actually not. It can only do a couple of transactions per second. And so we want to understand what does it really mean and where is the value and for which project it actually makes sense to use a blockchain. I want to give you some quotes just very quickly. I've been to Davos, this business conference, you could say, or a lot of politicians come there, and I was surprised by how many people there, this was actually in 2015, how many people spoke about this. And yet Christine Lagarde, who was completely aware of the issue, saying how virtual currencies could help with lowering remittance costs. You have Professor Welport, who just set up a $50 million fund in the UK to research blockchain for government usage. And Hermann Gref is maybe someone you may not really know, but he was the Minister of Foreign Trade under Putin for 8 years, and he's now the head of the largest bank in Russia. And he, for example, said blockchain is a technology that is capable to turn all the spheres upside down. The state regulation, functionality of the state and general finance, every single one, undoubtedly this is revolution. And this is just coming now from the politics sector. I could show you similar quotes coming from the tech sector of people like Andreessen Horowitz of those VC funds putting a lot of money into blockchain startups, and there have been billions invested over the last years in blockchain startups building solutions on top of this. And the last quote, then I will start with motivation, why it's important to learn about this topic. So Buckminster Fuller, which is a quote I think fits very well with all the stuff we are actually doing right now in blockchain. He said, you never change things by fighting the existing reality. To change something, build a new model that makes the existing model obsolete. That's what I feel we have partially done when building blockchain technologies, but also most of the projects in this space are doing. So they are often, it's very hard to just connect to legacy systems. It's about creating a new way of doing things in a purely decentralized fashion, using something we like to call crypto economics, meaning we have the means now to program incentives for people to do certain things. And based on this incentive mechanism, we create a protocol which works on its own, which is like a living thing which just continues to work without any central control. But it's a completely new paradigm, and you have to really think hard about business models and other things around it, how to make this work for you. Okay, this may be just as a quick introduction. I will now give you some definitions, and as developers, I think many of them are clear to you, and you have heard about them before, but I still just want to get on the same page for all those who are maybe not too much into maybe also cryptography or some basic things, that we understand those words, and once we have understood them, then I can explain you what a blockchain is. So first, a peer-to-peer network. So you know of the traditional systems, you have a host or server and you have clients. That's the traditional model. A client-server model, you have a hierarchy of clients serving data to server giving data to the clients. Then you have a model which is more decentralized if you have many of them. So at least if one of them falls out, the system still works, but maybe just a dozen of them. But what we are looking into is a completely distributed network where there is no client-server model at all, where every node has the same rights as the other node. You cannot even differentiate between the two of them. That's what we understand under peer-to-peer network. And this is, first of all, extremely robust, since there is no single point of failure. To shut down the network, you would have to shut every single node. That's actually why also there was an attempt, which some find even a bit funny, to put a Bitcoin node up in space just to make sure this node is always running. There is no state or country having control over it. And as long as this node is running, the network is live. And this just shows you how robust the network is. So it's really literally impossible to shut it down. All participants follow the same protocol. So there are a lot of definitions about what a blockchain is, and I will give you several of those today. One definition is, it is just a protocol. And there can be people implementing it in different programming languages, and as long as they are true to the protocol, they are part of this network. As long as you are not true to the protocol, you are automatically kicked out. So if you do something a little bit different, and there are a lot of rules to the protocol, some people also like to call it a fat protocol, if you compare to SMTP, HTTP, and all of those protocols you know of on the internet, which are not very big. They just have a couple of commands and how you interact with each other. But blockchain protocols are very thick protocols with a lot of rules, with a lot of incentive rules. And as long as you're true to them, you're part of the network. If you are one bit off, you're off the network. So since there is no single point of contact, you have also no means of censorship or no such thing as password forgotten, and someone can help you. So if you lose your keys, you lose your money. You lose all your rights, everything you had on this blockchain. There's nobody who can help you with this. So it's very base layer infrastructure. Where you can do where a lot of things can go wrong, did go wrong, and just yesterday, something also went wrong. Just yesterday, about $150 million lost, just because of a bug in a smart contract. So just to give you a feeling of what kind of things are happening if you make mistakes on a public blockchain. Huge losses. And nobody there really to help you. So nodes, of course, can be humans or machines. Like, we actually like to work on a machine-to-machine economy. We like to call the economy of things. To say, we have worked, for example, for a car manufacturer, and the idea is really to say, if the car has the ability to spend money or has a wallet, it can then pay the parking fees, it can pay for its electricity if it's charging, it can pay for toll collection, it can get paid when someone wants to use it and get from A to B. So I think this whole thinking of machines and robots being able to receive payments, do payments, enter into complex agreements, that's a whole new level. People always speak about we have billions of people who are unbanked, and Bitcoin is for them, this is true, but with even more unbanked robots, which we can help, get virtual bank accounts so they can interact in an economy of things. And this makes it possible to have really autonomous cars, because if just a car is self-driving doesn't really mean autonomous. It can bring me to an opera, but then it cannot even pay the parking fee, so it needs to drive around until it picks me up again, because it just can't do anything. So therefore, if we give machines the ability to interact on an economic level, make payments and receive payments, this is completely without any vendor lock-in or dependency on a single company. This gives us a great deal of security and abilities for the future. So this is just a peer-to-peer network which we are trusting. The next thing which should be familiar to you is cryptographic keys. But this is so important because there is no such thing as logging into a blockchain or logging into the system with an email and a password. I like to call those systems secure by default because everybody who interacts with it has to use public-private key infrastructure. And everybody can generate as many keys as they want to. There exists 2 to the power of 256 different key pairs. So there is, as long as you have a different random number as input, you always have a different key pair. This works very simple. So you get a different random number, put it into your key generation function in your implementation, your client, and you generate a key pair. The public key is something like your bank account number, which everybody can know. You can use it to receive money, and there have been a lot of even funny attempts. There was a guy holding his public key as a QR code inside a camera in a TV show and received about $30,000 just because people donated to him because he said he needs some money. And that's enough to send him something. You can just scan in the QR code and send guys some money. It's that easy. The private key, of course, should be held highly secure, encrypted, or even in a cold wallet which never touches the internet, or however you want to, but this needs to be highly secured. And the most attacks on the system are actually here, attacking people's private keys. So if you hear about that the blockchain has been hacked, this is actually not true. There has been no case of hacking of the blockchain in that sense that it was brought down in any sense. There have been hacking on applications on top of the blockchain, and there has been a lot of hacking going around private keys of exchanges and others who lost them, who have been not careful enough. And there have been millions have been lost because people just didn't store their private keys right. And if you lose your private key, you lose, of course, all the money you have on the blockchain. But once you have this key pair, how it works, you have a message like, I will pay $500 from Alice to Bob. You can then sign this message. And this part here, this signed message, is actually the only thing which makes it into the blockchain. So there's another definition of a blockchain. It is just a set of signed transactions. Just a set of signed transactions. That's this part. Everybody can review them and decrypt them and know the owner of the private key belonging to this public key has signed it. And I know this without knowing of the private key itself. And so everybody knows he actually wants to pay $500 from Alice to Bob. And that's all you need to know. And the private key can be stored securely somewhere else. And you can have a lot of those key pairs, often if in e-commerce, for example, or some companies who receive Bitcoin or Ether or other cryptocurrencies, they generate a new key pair every time they receive some money. So you cannot track them down or see how much money they have or something like this, because it costs you literally nothing or milliseconds of computing power to generate a key pair. So one key pair for each time you receive money is actually a good idea. You just need good software to manage all your keys. So that's one basic thing. Everybody interacts with each other over the blockchain through their keys. Next thing, which is very simple for you, a hash function. So you have some couple of bits and bytes, or could be 1 bit, could be terabytes of data. It goes through a hash function and gives you a hash sum. And we use this, of course, for absolutely everything in the blockchain. And we use a 256-bit hash, and there we can safely say there will never be a hash collision. I know of hash collision happening in 32-bit systems. It can actually happen. There is a certain likelihood. But for 256-bit systems, you can safely ignore hash collisions. To give you a feeling of how high this number is, so there is an estimation of the number of atoms in the visible universe, which is the visible universe is much more than this Earth, this Sun, this galaxy. It's a lot. And the estimation is 2 to the power of 72. It's the number of atoms in the visible universe. So 2 to the power of 73 is twice as much. 74 is again twice as much. And 2 to the power of 256 is such a large number that as long as you have a good hash function, you should never have a hash collision. If you would have one, this would be a real problem. Also for all the blockchain stuff I'm talking about. But this should be familiar to you. The next thing is a so not Merkle tree. And Merkle tree is just a way of how to store data. It's just a data structure. But a very important one, which gives you some very nice features. So let's just go through this very quickly. So unfortunately, I used plaque arrays on plaque ground, so you cannot see them. But there is a connection here, here, and always to the next hash, and here, and here. So you have those big data. You have this big data set. You put it in little chunks of, let's say, a couple of megabytes or even kilobytes. And then you hash them. 2 of them you hash together, and 2 of them you hash together, and so on. You have a tree, and you have a top hash in the beginning. So the first feature it gives you is that when you change one single bit in one of the data blocks, you get a different top hash. That's nice, but that you already would have gotten if you just hashed the whole data set. So that's nothing special. But what's special about this data structure is, if I want to prove to you that in data block number 2, there is data saying I own 5 bitcoins. If I want to make this proof to you, I give you this data set, a couple of kilobytes. I give you this hash and this hash. That's enough. Then you can generate this one, calculate this one out of those two, and out of those two you calculate the top hash. And the top hash is something which everybody knows. It's in the so-called block headers of the blockchain, very easily verifiable. And you can see, yes, this little piece of data is part of the bigger data set. I know for 100% now. It's called a Merkle proof. So I can prove someone with just a tiny bit of data that a certain part of the bigger data set is there, or that is really part of this data set, without giving him all the rest of the data. So that's what a Merkle tree can give you. So that's now enough for definitions. So we know what are cryptographic keys, we know what is a hash function, we know what is a peer-to-peer network, and we know what's a Merkle tree. And so in the next slide, I will try with one slide to explain to you what is a blockchain. So if you really understand the next slide, you can safely say, I know what a blockchain is. So let's go through this. So a blockchain is a chain of blocks. That's simple. A block is a set of signed transactions, and those blocks are cryptographically linked through a hash. That's the simplest explanation I can come up with. So let's try to explain what this means. So let's look at block 2 in the middle. There is a block header and actually a block full of transactions. In the block header, there are some numbers. The two most important ones are the hash of the previous block header and the Merkle root or top hash of all the transactions in this block. So as you saw before, we had those signed transactions. You put them in this data structure in a Merkle tree, which is a very big one, and there is this top hash, or top Merkle root, you could also say. This goes into the header and the hash of the previous block header. And this structure of how to store signed transactions is called a blockchain. And what does it give you? So let's say we are actually at block 3 right now, and someone wants to change one bit in block 1. Then the Merkle root would change of those transactions, so would the hash of the block header, and this link would be broken. Meaning nothing can be changed in the past. If I have this block 3, the past cannot be changed. If you want to change something in the past, you have to rebuild the blockchain from here. That's all you can do. But you cannot really erase something, or as long as I'm at a certain point, the past is certain. And this makes it tamper-proof, immutable, gives you all of those nice features which you need for financial applications, registries, or highly secured stuff, where you don't want to rely on any centralized party who could be malicious or tampering with it. So this is the simplest model of what a blockchain is. And the nice thing is every block is time-stamped. I mean, you have a certain time in block 1, 2, and 3, and you can say a transaction X, like he is sending money from A to B, he buying land, he buying some copyrights, music, all those things you can do with blockchain at time X. I can prove this. You can even use this, for example, when we are thinking about patents and stuff like this, and just write something up, a PDF, hash it, and we set it in the blockchain. This is a proof that at this point of time, this document existed in this form, and that I put it there because my cryptographic key signed it. And I don't know if it would hold in court, but theoretically, it is a secure proof that this document existed at this time. And people use it for exactly this, saying if they have financial documents, they hash it, put it in the blockchain, and this is like a secure storage. Because if you just put it in your own database, it can be erased, it can be changed, just because someone wanted to change some numbers. You have no security that at this time, this document existed exactly in this way, in this format. But here you can do this, because it's a decentralized database, nobody can play around with. So I already spoke about transactions, but I just want to mention again, this part here, the signed transaction, this is the stuff which goes into the blockchain. So that's why a blockchain is just a set of signed transactions which are combined in a block, and those blocks are cryptographically linked to each other with a hash. What is the information in a transaction? So a transaction has, of course, a sender, where it comes from, the one who signed it, a receiver. It has usually an amount of virtual coins. In Bitcoin, that is Bitcoin. In Ethereum, it's Ether. And there are tons of other blockchain. They have other coins. And it also has some data. And this gives you some interesting features. You can put arbitrary data in it. And this data can then be used, what we will speak later about, to call something we like to call smart contracts. I will get to the point what smart contracts are. But at this point will be very crucial. So now the next question. How are new blocks created? So we have this nice structure now, but if everybody can create new blocks, or only a small party can create new blocks, then they could censor it and say, I'm only allowing the transactions I like, or people could completely spam the peer-to-peer network with new blocks, and what is the next one? So this is the real problem Satoshi Nakamoto had 2008 when he started Bitcoin, saying how to solve this problem about who's allowed to create the new blocks. And there's a lot to it, but it's called proof of work, but it comes down to this simple rule. This is of course a bit oversimplified, but it gets the point across. The rule is, as long as the hash of the block header is smaller than this number, so 2 to the power of 256, very high, divided by difficulty, then this block is valid. That's the only rule. So what does this give us? So a miner is a part of the peer-to-peer network. He gets all those signed transactions which are floating around there, creates a block saying, I'm checking those transactions, they are true to the protocol, nobody is spending their Bitcoin twice, every transaction is valid, they have enough that they can actually spend those Bitcoin, done. Then there's one number in the block header called a nonce, and this number they can set to whatever they want to. And they set it in the beginning to 0, hash it, and usually the hash is larger than this number. Okay, then they set it to 1, hash it, and check again. Set it to 2, hash it, check again. And there are large mining farms or computing center in Iceland and China and the US and everywhere in the world doing nothing but hashing. So you could think about a high waste of energy, and actually some kind it is. The energy consumption of Bitcoin is higher than the energy consumption of Cyprus, a whole country. And even for Ethereum, you need more than one nuclear power plant to just pay for the mining energy. To just give you a feeling of how much energy is going in there. And this energy is not used to actually calculate transaction or doing something useful. It's just hashing, securing the blockchain with proof of work. And they all do this. And then there is this difficulty. The difficulty rules is very simple. So for Ethereum, for example, the block time is, also the time between two blocks is around 14 seconds. And every time someone finds a new block, before the 14 seconds are over, the difficulty slightly increases. If he finds a block after 14 seconds, then the difficulty slightly decreases. So it becomes easier to create a new block. And with this, in average, you always have this 14 seconds in Ethereum. In Bitcoin, you have 10 minutes. So on average, every 10 minutes, you get a new block. Sometimes it's 1 hour, sometimes 1 minute, but on average, 10 minutes for Bitcoin. So this is a simple rule. So they all hash it, and when someone finds a valid block, which fulfills this rule, he sends it to the network, everybody checks the transactions, see, yes, they are valid, checks the hash of the block header, yes, it's smaller than this number, I agree, let's take this block and it's a valid one, and we continue mining on top of this one. This makes it very secure that nobody, or almost nobody, can attack the network. There are still attacks possible, I will come to this later, but this is what is securing the network in a decentralized way, that there is no central control governing it. So now there is something called forks. You may have heard of that, especially in Bitcoin, but also for Ethereum. So what is a fork? So there are some normal occasional forking which is happening all the time. Meaning there is one miner, let's say in China, one is in the US, they both have block 1, they tried to create block 2, and they created within a certain latency time, because it takes some time to send blocks around the world, and everybody receives it, both create block 2. So at this point in time, both blocks are valid. Both are valid blocks. What is the truth? And at this point, actually both. But some miners continue to mine on top of this block. Some miners continue to mine on top of this block. And someone will find the next. And as soon as someone finding block 3, he will publish it, everybody knows it, and then this is the valid block. And this is the only valid chain, and this is completely ignored. I forgot something very important to mention in the last slide of the proof of work, why people actually are doing this. Actually, this is very important information. So they are doing it because they get a reward in Bitcoin. So for right now, for every Bitcoin block you're creating, you get 12.5 Bitcoin. 1 Bitcoin is around $7,000 right now. And that's the money you get if you create a block. So there is an incentive in the protocol itself to do such a thing. For Ether, it's very similar. There you get right now 3 Ether per block plus transaction fees. And that's the reason people actually are doing this. As soon as their energy costs are higher than the money they get, they switch their miner off, and the difficulty then also decreases. But if the reward is higher than the energy cost, it makes sense for them to turn on their machine. So there is an economic incentive to do things. And that's actually, for all the blockchain applications, it's about crypto economics or about economic incentives to make people behave in a certain way so that the system works. So let's get back to those blocks. So those miners are creating those blocks, and some have occasional forking from time to time, not really a big problem. Very rarely, there's also a longer forking, and that's why people say for Bitcoin, for example, you should wait at least 6 blocks, so 1 hour, before you are 100% certain your transaction is actually in. Because it could be you're just on a fork and someone will publish a longer one later, so just let's wait a bit. So the finality of your transaction increases over time. The longer you wait, the more certain you can be your transaction has made it in. And this also shows you now one attack vector, so something we like to call the 51% attack. Imagine the following. I want to buy something, let's say a nice car, paying in Bitcoin here in block 2. And that's all the people see. This one is completely hidden for now. This is something I do on my local machine because I have more than 50% of the hashing or mining power. So I'm computing those blocks, but I don't let anybody know about it. It's just on my local machine, not published. So people see block 2, I'm paying in Bitcoin, get my car, and he says, okay, let's wait a couple of blocks to see you're certain. You wait until block 5, everything is good, I drive away. In the meantime, in block 2, I spend the same Bitcoin for something else, or just send it to another account which I own. So the Bitcoin are now gone, so this transaction here, buying the car, is actually invalid, because I actually spent the same Bitcoin here for something else. I have more than 50% of the mining power, I continue to create a block, and I am a bit faster than the other, so I can create more blocks. And once I have a longer chain than all the others, I publish it all at once. Everybody sees this is actually a valid blockchain, this is invalid, this is a higher block number, and this is all correct. So I got my Bitcoins and I have my car. And this is like a double spend attack. So if someone has more than 50% of the hashing power, there is a danger that such a thing can happen. Therefore, it's very important that this power is very distributed. And usually if something happens which looks like there is people creating alliances or mining pools becoming too big, sometimes even the price goes down, so people go away from it again. Because miners, of course, have an incentive that the system is actually working, and doing such a thing would hurt the system, and thereby mostly also their value, because they have most of their value in virtual coins. So this is one thing about forks. There's also another reason why forks are actually something good. If you want to change the protocol, then you need to make a hard fork or a soft fork. So there are two kinds of forks. So first, let me explain you the hard fork. Hard fork just means you make a change of the protocol which is not backward compatible. For example, in Bitcoin, there is a rule saying one block should not be bigger than 1 megabyte. And since years, there is a huge discussion about if 1 megabyte is too small or even too big, because every block is full of transactions, actually they would need bigger blocks. But some argue it doesn't make sense to make them bigger because of different issues, size of the database and all of this. So, but if you want to change this rule from 1 megabyte to 2 megabyte, that you allow for 2 megabyte blocks, then every single node in the system needs to upgrade. Because their node would not accept a 2 megabyte block. So therefore they need to upgrade. So if you make this change, everybody follows the new rules. Of course, if some miners say, no, I don't like this change, I continue on the old chain, well, then you have two blockchains. And this is actually the case also for Bitcoin. There's something called Bitcoin Cash and Bitcoin, because just this summer they make a split. They couldn't agree on a block size, so they said, let's split. We fork off of the main chain. And this month it will happen again, because there's again a group which says, no, the Bitcoin protocol should look a bit different, and they split off. For Ethereum, this also happened. There was one very contentious fork where there was not a clear agreement on what to do, and now we have Ethereum and Ethereum Classic. So as long as the community doesn't agree, they split off and mine on their own chains. And people who had Bitcoin before this fork have now Bitcoin and Bitcoin Cash afterwards, because they are still valid on both chains. So it's a bit confusing for mainstream users, but technically it's not a big deal to have a couple of chains, as long as you have one which looks like the main chain, which people easily could use and trust. But then there's also something we call soft forks. This is when you make rules where the old ones are still valid, and you just basically shrink or make them harder. For example, if you would say the Bitcoin block should be 0.5 megabytes, so even smaller. So as long as the majority of the miner says, I'm only taking in blocks which are smaller than 0.5 megabytes, then they would make a soft fork, and there would be no new blocks for the bigger ones, because all the majority of the miner is using smaller blocks, but the old clients don't need to update, because if I run a Bitcoin node, those smaller blocks are still valid for me, so I don't have any need to upgrade. I'm on the same chain. So for soft forks, you will not have a split. It remains one chain, but the bad thing about it, only the miner decide on certain things, so they can censor stuff or do whatever they want. So soft fork is miner controlled, hard fork is more user controlled. That's why I actually like hard forks more than soft forks. Okay, so much about forking, and now let's try to summarize a little bit what we have learned. So one definition out of the many, which I also like, is calling blockchain a distributed permission ledger. Distributed because you have this database on many places. So for Ethereum, it's about 20,000 nodes. For Bitcoin, it's about 5,000, 6,000 nodes. They store this database, so it's distributed. Permission, because it stores who is allowed to do what. In the case of Bitcoin, it stores account balances, you could say. It doesn't store directly the account balances on-chain, but it stores the transaction, which it then can use to calculate account balances. But you know that Bob is allowed to spend 5 Bitcoin, Alice is allowed to spend 10 Bitcoins, and so on. So it stores this permission. For Ethereum, it also contains those information, account balance. But it also contains data. And now the most important thing, and that's the big changer, which changed actually everything, is it contains logic and code, conditions. And that's something we like to call smart contracts. So what is a smart contract? A smart contract means you have a little bit of code attached to an account. And every time this account gets a transaction, this code gets executed. This code could look something like this. If time smaller than this, then send the money to him. If time is bigger than this, send the money to him. Or based on some other conditions I'm reading from this blockchain, I make a decision where I should send the money, or how I should store the money, or votings. You can say there are token-based systems. You create another virtual currency within a smart contract, making a vote on what should happen with the money. And there's many, many things you can think of. Or another example is something we like to call multi-signature wallet, that you don't store all your Ether in one key. You say, no, I make a smart contract. So I, for example, did store my Ether in a smart contract. And there are rules saying I'm only allowed to spend X amount of Ether per day with one key. If I want to spend more of this, I need 2 of those 3 keys. So I can have 1 key in a hot wallet, and if someone gets this key, well, and if I see it and he takes money out of my account, I have the 2 other keys in a secure place to replace this other key. So I have like built-in security within the smart contract. Or I could, for example, program how much money is my wife allowed to get per month, how much money should my kids get. I could have like a programmable bank account. And that's actually one of the main topics, or one of the key takeaways of today. Ethereum is about programmable money. For the first time, you as developers can actually have real cash, which is digital, which you can program. So not, I ask the PayPal API, did the money come through, or the Visa or MasterCard. That's not, you don't need to depend on this. You just say, I received the transaction, I can verify it myself on the machine, on my desktop, on my mobile, or in my car, or on IoT devices. I received the money. Once I received it, I have it. There is no thing as like a refund, or I have to give the money back because there are some claims. It's like cash. And you can program it. And one of the killer applications right now in Ethereum is something people call ICOs, or initial coin offerings. They're a way of crowdfunding projects. You just say, I give people a token, so I create like an own virtual currency, or shares, or whatever you like to call it, or utility token, depending on your use case. And people pay for it, and you have money to build a project. Of course, you have to be very careful there, because all this blockchain space is a bit like a Wild West right now. There's a lot of scams out there, people trying to take your money, a lot of bugs happening in smart contract. As I said, just yesterday, people lost about $150 million because of a bug in a multi-sig smart contract. So there are many, many things which can and will go wrong and did go wrong. So you should still be very careful. It's very early days. But just to see the power of this application, that you can do such a thing as a developer, is something very huge and potentially game-changing, because you can do such things as registry or every financial constructs without any middleman, peer-to-peer. It's a system which removes the intermediary. You have a smart contract, both can read it, both can interact without even knowing each other or trusting each other. I don't know if you can read this, but I wanted to show you one example of how simple a smart contract can be. A smart contract is not something very complicated, big and huge, of thousands of lines of code. Usually it's about 20 to 100 lines of code. The big ones, 200, 300. And this is just one very simple example of a smart contract implementing a coin. So if I want to make my own virtual currency, I say I store something called the minter. So this is one public key or an address about who's allowed to create coins. And I store the balances of users. So there's a mapping from address to unsigned integer saying which Ethereum address has how many coins. That's all I need to store in my smart contract. Then I have something here is the constructor. So it's the same name as the contract, is this function coin, saying minter equals message sender, meaning when I deploy the smart contract on the chain through a transaction, I am the message sender and I am set as the minter. And there is no way of ever changing this again because there's no line of code saying the minter can be changed. So I will be forever the minter, the one allowed to create coins. That's just my contract. So then there are two functions. One is called mint, one is called send. One is saying mint as two parameters, receiver and amount. And it says if the message sender is not the minter, return. Because also something to be aware of, every smart contract, every function, everybody can call. So that's a huge attack vector. Every guy out there in the world with a computer, every hacker, everyone who sees it, can look on the blockchain, check your smart contract, and call every function you have in there. That's something to be aware of. So here I'm checking if the message sender is not a minter, return. So nobody who calls it will do nothing except of me. If I'm calling it, I can increase the balance of the one I call receiver by amount. So plus equals amount. So I can give someone coins. Let's say they pay me in cash, I give them some coins. You could also make, I didn't do it because I don't have enough place, make a function called buy, and if they send some ether to this function, they get some coins automatically. Could be another way of doing it. I just didn't do it because I don't have enough space here. Then there's a function called send, where also everybody can call with receiver and amount as parameters. It just checks if the balance of the message sender is smaller than the amount he wants to send, then return. So if you don't have enough money, you can't do anything. But if you have enough coins, then decrease my balance of message sender by amount and increase the balance of the receiver by amount. And that's it. And you actually don't need this last line. It's just the optimization. So with this, you created your own coin. And it's decentralized on this database, runs forever, nobody can ever change it, and you can use it for whatever you think it's useful for. Of course, you can put a lot more features in it, like there should never be more than 10,000 coins. Let's say you make a concert, a music concert, there are 10,000 tickets, and you have this rule and you don't sell more than 10,000. Once you have sold those 10,000, they can freely trade them, sell them, do whatever they want with it, but in the end, it will only be 10,000. And if they come and want to go into the concert, they have to send you one coin and then they can get in. So it's just one way of doing this, and the nice thing is, it's like a big open API. Everybody can build applications on top of this. Let's say let's say use this for music tickets, concert tickets, and someone builds a trading platform for tickets. They can, just using the smart contracts. They don't need even to talk to you, because you have given them the interface to build it. And it's a secure one, and they interact with public and private keys. So all those smart contracts are building something like I call Ethereum one big open API. You open up your applications, but securely. Everybody can read it and use it. So those smart contracts are Turing complete. I say quasi Turing complete because there's one constraint. There is not much space in the blockchain and also not much time for computation. If you think about the Ethereum blockchain as one big vault computer, like a shared computing system we're all using, which compared to the cloud where there's a shared database, Ethereum could be seen as a shared computer where we compute things together, or at least highly redundant. Everybody does the same computation, we agree on this. But still, there is something we call a block gas limit, so there's only a certain amount of computation you can do within one block. So you cannot do a forever loop or other things like this. That's why it's quasi Turing complete. Of course, there's secure interaction, and contracts can build on other contracts, they can send transactions themselves, they can actually create other contracts, they can retrieve data from the blockchain of like what's the current time, or they can retrieve data from other smart contracts, so it can be nicely built on each other. And so we have built smart contracts, for example, which manage the access control to smart locks. So if you have a smart door lock, and you can manage in a smart contract who's allowed to exit it. We want to use this for renting it out in like Airbnb-like, renting out your apartment without any middleman. And then there's another smart contract from another company doing insurance. So you could do insurance on demand. As when he locks into the door because he has paid the lock to get in, he automatically has paid the insurance, even has paid the cleaning lady, and she also has access in this time frame to do her work. So you have everything automated, and you can interact with all those other services and smart contracts around you. Okay, my time is actually almost over. I wanted to give you one last slide. So what is Ethereum? I like to call it an open source platform to build and distribute decentralized applications. And give you this one technology stack in the end. We only talked about one little piece here. Think about, you have the internet, you have hardware running it, like hardware clients, like phone or my computer. We just talked about the Ethereum virtual machine, so the stuff which runs the blockchain and the smart contracts. But there are also protocols like Whisper, which is a decentralized messaging system. So I like to call it WhatsApp without WhatsApp, where you can have encrypted messages you send to each other with even routing privacy. So you don't know where it comes from and don't know where it's going to. I don't have the time to explain this to you, but you have a decentralized message system, Swarm, or also another system called IPFS, a decentralized storage system, where you can store data, highly redundant, and pay people for hosting your data. Also, of course, encrypted and in a peer-to-peer network. And if you have those three protocols, you can build purely decentralized applications, something we like to call dApps. The applications with zero infrastructure costs for the one who is publishing them, and you have the users paying microtransactions to actually use the system and pay, for example, the hosting fees in Swarm, which are the many users storing, let's say, your interface files. And one last slide, which is the same picture as before, just in a different way. So you have those circles represent 3 users, so they're all 3 identical. And you could think about them, they interact over the blockchain when it comes to money, when it comes to, let's say they play a game together, with everything they need to consensus, but they don't trust each other. That's what they do there, consensus. Then they use Swarm to send around bigger files, for example, the HTML, CSS, and JavaScript files hosting the user interface. So they get the user interface from this decentralized database. In their browser, which is Web3 enabled, they can talk to the blockchain, and they use Whisper to send peer-to-peer direct messages to each other, because you cannot do everything on-chain, because it would be way too expensive. And if you have this system, you deploy an application which just runs forever, and if you have done the incentives right, that let's say you get a 5% fee for every time people use your application, Swarm guys get a little bit of money for hosting it, and they can have other rules in there, then you have created an application which is 100% decentralized. And that's what we call the Web 3.0. If you think about the Web 1.0 or like static websites and just getting some information, Web 2.0 with JavaScript, you got all those social media and e-commerce, all those things going on where people can interact with each other, but it was always just about data. And with Web 3.0, we speak about the internet of value and exchanging agreements, exchanging money, and this completely decentralized. That's what we like to build. That's what we call the Web 3.0, and that's what actually Ethereum stands for. And happy for anybody to join using this great technology and building applications on top of it. Thank you for your attention.